Hello student, how are you? I'm Arunsir. Welcome to my channel Tuition Expert. Today in this class, I'll teach you the work, energy and power. This is best NEET crash course. Student, if you watch my video regularly and follow my class attentively, then I can assure you that you must crack the NEET exam confidently with a good rank. Now let's start about the class. So today's class is work, energy, power. Work, energy, power in one shot. So suppose this block, the force F is applied on the block at an force is applied at an angle theta, and due to the force applied, the body is displaced from A to B, from this position to this position, and the displacement is S. So, what is the work done by the force? Work done by constant force is F S cos theta, which is equal to F dot S. So this is the work done by constant force. When force is constant, F dot S. If F and S, F force and S is perpendicular, then the work done equal to 0 because theta equal to 90 degree. Suppose a man carry a bag. What is the work done by the man to carry the bag? Here weight mg act in this direction and displacement is in this direction. This angle is 90 degree. So work done equal to 0. So work done equal to 0. Work done may be 0 by either force is 0, displacement is 0, and angle theta is 90 degree. So work done equal to 0 for three cases. Force is 0, displacement is equal to 0, or theta equal to 90 degree. Any factor is 0, then if any factor, that is force and displacement, any factor is 0 and theta equal to 90 degree, then work done equal to 0. Now force versus displacement graph. If a constant force act, then work done equal to area of fx diagram, that is force versus displacement diagram. Area of this diagram represents the work done because f is length, x is breadth, so length into breadth is area. So force versus x diagram is this. This is x, this is f. Suppose this is 10 Newton, 2, this is in meter, this is in Newton, 2 meter, 4 meter, 6 meter. What is the work done? Force is applied. Force versus displacement diagram is this. Now what is the work done to displace 6 meter by this force? Here force is variable force. Force varies up to 2 meter linearly, then constant force, then force is decreasing, but the total work done to displace the body up to 6 meter equal to area of this figure. So now you can calculate the area of this diagram, which is trapezium. So work done equal to area of fx diagram, which is equal to half sum of the two sides, that is this side is 6, this side is 2, into height is 10, so 40 joule. This is the force. Work done for variable force equal to integration of f dot dx. This is the work done for variable force equal to f dot dx, where f is the force at the moment when displacement is dx. So what is the example of this? Suppose force acting on a body varies as f equal to 2x when x 3 less than 1 equal to 10 when x less than equal to 5 greater than 3 and x minus 3 when x less than equal to 6. Suppose this is an one example. Force acting on a body varies as this. Force versus displacement diagram. Force versus displacement. The relation between force and displacement is given as according to this. What is the work done? What is the work done to displace the body from 1 to 6 meter? So what is the answer? Answer will be this work done equal to. So this is the variable force. So we apply this theory. Fx here force and displacement. Force is along the direction of x. It is given when no other when it is not mentioned it is not mentioned the angle between f and dx. Then we consider that f and dx angle between f and x is 0. So work done equal to f dx from 1 to 3 plus, so f dx. Now what is f equal to 2x. Here from 1 to 3 force is 2x. Now 3 to 5, what is force? 10 dx plus 5 to 6, what is f dx. Now integrate this and find put the value of this. We put the value, we get the work done. One end of the spring is attached in a wall and other end of the spring is pulled by an external force. So suppose this is the natural length, and when force is applied, then external force, when force is applied, then spring extends. So external force here, F external is proportional to displacement. That is, as more we extend, force applied also be more. That is, external force is proportional to displacement. Now F equal to minus kx. Here here displacement is in this direction and external force is in this direction. So work done is positive for external force, but spring force act on the spring is in this direction. Spring force act in this direction. So spring force equal to minus kx. This is spring force. Spring force equal to minus kx. So external force and spring force must be equal for equilibrium. This so external and spring force. So we extend the spring with such that the external force is always the spring force, such that we can extend further. So external force must be equal to spring force such that we can extend further. So external force equal to kx, and it is positive because here this force and direction of x is along same direction, but spring force is along this direction. So spring force will be minus kx. When we extend, then spring force minus kx, and when we compress, then also spring force is minus kx, because suppose this is the spring and we compress this. So when compression take place, this is x, when compression take place, spring force act in this direction. So here also spring force is opposite of x, f spring. So spring force is always opposite to the x. So spring force is always minus kx. Now what is the work done by the spring? Work done by the spring, W equal to work done here for variable force f dx, x1 to x2. So f equal to kx dx, x1 to x2. Now work done by the external force, equal to potential energy of the spring. Work done by the external force equal to potential energy of the spring. So this equal to k x dx equal to k x square by 2, which is equal to half k x2 square minus x1 square. So to extend the spring from x1 to x2, the work done equal by external force equal to this, which is stored as potential energy on the spring. So to extend, suppose this is x1 first and this is x2, this is x2, x1 and this is x2, this is x2. So what done for this? So what done for this? This is x2 minus a. What done for this? What is the what done? What done for this? What done to extend from this to this equal to half k x2 square minus x1 square. So this is the formula. What done to extend from x1 to x2 equal to this. Now if x1 equal to initial x1 equal to 0 and x2 equal to x, then we get so what done equal to half k x square if x2 equal to x and x1 equal to 0. That is when the string starts from natural length and extend up to x, then x2 equal to x and x1 equal to 0. So half k x square. This is the potential energy of the spring to extend x from its natural length. That is when x1 equal to 0 and x2 equal to x, then we get w equal to this. So this is the potential energy of the spring. Suppose a spring constant is extended up to x, then it is further extended to y. First it is extended up to x, then it is further extended up to y. Find the work done. To extends in second step. That is second step. When it is further extended y, for that extension, what is the work done? So here answer will be work done equal to half k final. Here final x2 equal to x plus y, because it is y is further extended. It is written as further extended. That is the here first x is x, that is x1 is x, and then it is further y, that is y. So x2 equal to x plus y and x1 equal to x. So minus x square. So this is the answer. So this is the answer. Now work energy theorem. So by this theorem is very important. By this theorem we solve the problem on work energy power. So what is the work energy theorem? Suppose a ball of mass m is moved with velocity u. Now a force F is applied on the ball and it moves up to x, and after traveling the distance x, the velocity is v. So here work done by external force equal to what? F into x, because force is in the direction of x, force into x. Now we prove that work done by external force equal to change of its kinetic energy. So F equal to ma into x. Now we know the equation is v square equal to u square plus 2x. So ax equal to v square minus u square. So m into x equal to v square minus u square by 2. That is half m v square minus half m u square, which is kinetic energy final minus kinetic energy initial. That is we change of kinetic energy. Del means change. So work done by external force equal to change of kinetic energy. This is the theorem. Work done by external force equal to change of kinetic energy. Net work done on body. Net work done on body equal to change of kinetic energy of the body. Net work done means work done may be positive and may be negative. So we calculate the algebraic sum of or down. Suppose a body is here and body moves with velocity u in this direction, and a force F1 is applied in the direction of velocity, and friction acts in the opposite direction, and also external F2 act in this direction. So here, after traveling the distance, if final velocity is v, here what is the work energy theorem of this case? F2 is act, friction force act. So what is the work energy theorem of this case? Here net work done equal to, that is work done, we calculate positive and negative work done. Positive work done, which one is positive work done? When the force applied is along the direction of velocity, then this work done, then work done by this force is positive. So F1 into x, this is positive work done. And F2 is opposite to the velocity, initial velocity, opposite to the initial velocity. So F2 work done, F2x cos 180 degree, cos theta, because F2 is in this direction, x is in this direction, so cos 180 equal to -1. That's why it is negative work done. It is negative, and friction also negative work done. F into x cos 180, so we get, so we can write minus minus if we this. So this is, that is the force which act in the opposite direction of initial velocity. The work done by this force will be negative. So this is the net work done, and this net work done equal to change of kinetic energy, that is half m v square minus u square. Right side we always write final kinetic energy minus initial kinetic energy. So this is the work energy theory. Now, this is a wall. Here a spring is present. Spring constant k equal to, suppose, 100 Newton per meter equal to kx, Newton per meter. Now a ball of mass 5 kg moves with velocity 20 meter per second, strikes the spring. Here, suppose, here friction this road, this path is rough surface, and coefficient of friction is given 0.1. This is smooth. Suppose this is smooth. Okay, this is smooth. Now if the ball strikes the spring, what is the compression of the spring? If ball strikes the spring, if ball strike the spring, what is the compression? What is compression of spring? This is the question. If this ball strikes the spring, what is the compression of the spring? Here spring constant is given, initial velocity of the ball is given, mass of the ball is given 5 kg. So solution, this type of question we use work energy theorem. We apply work energy theorem, this problem. So work for energy, any problem can be solved by work energy theorem. So here we apply the work done on the ball. So here ball is the main substance. We apply work energy theorem on ball. So what is the theorem? Change of kinetic energy. Right side net work done. Left side we write net work done on ball, and right side we write change of kinetic energy of ball. Now net work done equal to what? Here when the ball moves in this direction, friction force act in this direction, when ball moves in this direction, friction act in this direction. So work done by friction equal to negative minus mu mg into, and this path is, length of this path is given, suppose take it 8 meter. Now work done equal to mu mg into distance 8. Now when the ball strike the spring, then the spring force exert on the force in this direction. So work done by the spring, by the spring on the ball will be negative, because when the ball is strike here, so finally suppose ball comes here velocity equal to 0. Now when the ball approaches to the spring, then spring force act which direction? Spring force act in this direction. This is spring force. So movement is the movement of the ball is in this direction and spring force act in this direction. So work done by the spring on the ball will be negative. So what is the work done by the spring? Spring exert the variable force. So work done by the spring will be half kx square, half k into x square. So this x is the compression of spring. Compression of spring, half kx square, and this is smooth. So this is the net work done on the ball. Now change of kinetic energy. Final kinetic energy is equal to 0 minus initial kinetic energy half mass into u square 20 square. So from this equation we get x. From this equation we get, because negative will be cancelled, put here value, you get this. So from this equation you get the value of x. Okay, here negative work done is work done by the friction and work done by the spring, both will be negative work done. And energy, change of kinetic energy, final kinetic energy 0, initial kinetic energy this. Conservative definition is the force under which work done on a body for a closed path is 0. This is the conservative force. Example, gravitational force, electric force, magnetic force. This type of force is conservative force. That is net work done under closed path. Work done under closed path is 0. That is cyclic path, f dot dx will be 0. So f is conservative force. And example given. So how can we find that? For conservative force, net work done by the closed path is 0. Suppose take the example of gravitational force. Suppose a body is in the ground and it takes at a height h. Mass of the body is m. So what is the work done from A to B? Work done from A to B, WAB equal to by gravity force. We consider work done by gravity force. Work done by gravity force. So work done by gravity force. Gravity acts in this direction and displacement is in this direction. So work done by gravity from A to B is equal to mg into h into cos 180. Because mg act in this direction, h in this direction, so work done by the gravity to displace from A to B is this, that is minus mgh. Now when the body is displaced from B to A, that is closed. Now work done by B to A equal to what? Now when the body comes from B to A, then gravity acts on this direction. So gravity mg and h cos 0 degree. Now when the body moves from B to A, then mg act in this direction, h in this direction. So mg into h into cos 0, which is equal to mgh. Now total work done, AB plus BA equal to what? 0. So for closed path A to B and B to A, closed path total work done is 0. Del U equal to change of potential energy equal to minus work done. So here we show that change of potential energy equal to minus work done. What is this? Work done is work done by conservative force. Work done by conservative force. This work done is work done by conservative force. So when a body, in this case, suppose when a body is displaced from A to B, suppose body A to B, what is the change of potential energy? Change of potential energy mgh minus 0. We know what done. We know the potential energy at here at a height h equal to mgh. So change means final minus initial. At ground potential energy is 0. this is ground. So change of potential is equal to 0. Now what is the work done by conservative force? Work done by gravity from A to B equal to minus mgh, minus mgh. So minus of work done equal to minus mgh, that is this is satisfied. So del U equal to minus W, this theorem is applicable for conservative force. Work done here, W equal to work done by conservative force. Del equal to change of potential energy, change of potential equal to minus W. Work done equal to F dot dr. So if F and dr is in same direction, special case minus F into dx dr, this is du for special case. So F equal to minus du by dr, this is a formula. Force equal to minus du by dr. Here u is, here u equal to, here equal to potential energy of the body, potential energy of the body. So when potential energy of the body is given in the function of r, when F is given in the function of r, then when u is given in the function of r, then to calculate the force at any position, we apply this theory, minus du by dr. Force equal to minus du by dr. Okay. Now the force under which net work done for a closed path, is not zero, is not zero, that is F dot dr not equal to 0. This is non-conservative. Example friction force. Suppose this is a ground, a block is displaced from A to B, A position, this is B, BC. So mass m. Now this displacement is S. Suppose S is the displacement. Now when the body is displaced from A to B, then the friction force act in this direction. And displacement is in this direction. So work done from A to B. What is the work done by the friction? When the body is displaced from A to B, what is the work done by the friction? Not work done by the external force. Work done by the friction equal to minus F into S, because Fs cos 180 means minus Fs. Now when the body is displaced again B to A, WBA. Now when the body is displaced from B to A, then the friction force act in this direction. So from B to A, again minus F into S. So total work done by closed path, WBA equal to minus 2Fs, which is not equal to 0. So the topic is work done. How to calculate work done by variable force? In a space. Work done by variable force in a space. Suppose a body is at here, this position is x1, y1, z1. Now a force act in this direction, the force. So body displaced from this position, whose position is x2, y2, z2. So what is the work done to displace the body from A to B by the external force F? Now the F is, suppose this is variable force, because x, y, z is not constant. X, y, z is changes with position. So this force act on a body, displace the body from A to B. What is the work done? Now here work done equal to, we know, F dot dr integration. So F means xi plus yj plus zk dot dr. Now we take dr as this. Dr equal to, actually dr, r equal to, we know r position of a point, position vector of a point is xi plus yj plus zk. This is the position vector. Now dr equal to dxi plus dyj. So we put dr is this. We put dr equal to this. So we put dr equal to this. Now the position, initial position is this, and final position is this. So now if we multiply, this is dot product. If we multiply, then what we get? X dx, this into this, x dx plus y dy plus zdz. Here different variables x, it may be x square, it may be 2y. So here the not only power x y 1 it may be x square, it may be different variables, different power, it may be different power. So procedure is this way. Now this is, now we can find this integral. This is x square by 2. When we apply, when we put this value, then we only put this value x1 to x2. When we put this is x1 to x2, and y square dy, that is y1 to y2, and z square by 2 z1 to z2. We only put x coordinate in terms of x, in the place of x, y position in terms of y, z position in the terms of z, in z coordinate in z. So this is the work done by variable force in a space. That is when the position changes from one position, when the position of a body change from one to another position, then we can apply this. And work energy theorem is applicable for any force, conservative and non-conservative and external force, for any force. D equal to minus f dot, f equal to d by dr, minus f dot dr, d equal to minus f dot dr is applicable for only conservative force. For non-conservative force, this formula does not hold. For non-conservative force, this does not hold. D equal to minus f dot dr not equal to minus dot dr for not equal to for non-conservative force. For non-conservative force, what work energy theorem is applicable for any force, then the general theorem is work done by conservative, work done by non-conservative, work done by external force equal to always change of kinetic energy, always change of kinetic energy. So here left side is net work done, actually net work done, this is net work done, and change of kinetic, right side is change of kinetic energy. So when a, suppose a body is in the ground, smooth ground or rough ground. Suppose a body is displaced from this A to B in a rough ground. This is rough, that is friction is present, mu is present. Now a force is applied on the body, velocity u and final velocity v. So what is the work energy theorem for that case? Here change of kinetic energy equal to half mass is suppose m, half m v square minus u square, and here conservative force. What is conservative force? Here gravity is the conservative, gravitation act in this direction. So work done by the conservative force is 0, wc is 0. And what is non-conservative force? Here friction force is non-conservative and non-conservative friction force. So friction force work done by the friction force equal to minus f into displacement is x, f into x, and this is non-conservative force. And external force, here external force is f, so f into x, this is external force. So this equal to this theorem. So work energy theorem is applicable for any force, and this is the general case, general theorem. Conservative, wc for conservative and wnc for non-conservative. And if any external force is act, this is external force, external force, work done by the external force. these are what done. These are the work done by conservative. This is the work done for by non-conservative. This is the work done by external force equal to net work done. That is left side is net work done and right side is change of kinetic energy. A ball is present at a height h1 and suppose this is the problem. A ball of mass m is present at a height h1 and it is pushed little, then it moves. This is smooth surface and this is also smooth surface, and the ball slides along the inclined plane, then it moves the distance, then it moves for rough path through the distance x and climbs in this smooth plane. And when it after climbing this tower, what is the velocity of the ball? What is the velocity of the ball? So here, what is the velocity of the ball at this position? So here it starts from 0. What is the velocity of at this position? So this type of problem, how can apply? We apply the work energy theorem. We apply the work energy theorem. What is the work energy theorem? Net work done, left side net work done equal to right side change of kinetic energy. Left side we write net work done, right side we write change of kinetic energy. Now net work done, what? Net work done equal to here which force act? Here gravity force act and a friction force act. Now when the body moves from this to this, what is the gravity force act? mg into h1, mg into h1. Now when body moves from this to this, what is the work done? Work done is by the friction force, which is negative minus mg into x. This is the negative work done because friction is always negative. The body moves in this direction, friction act in this direction, so work done by the friction is always negative. Now when the body climbs when the body climbs from this to this, then gravity act in this direction and it moves in this direction. So when the body climbs, then the work done by the gravity also negative, so minus mg into h2. Now h1 is enough, h1 is more than h2. So now right side we write half m v square minus 0. So from this equation we get the v. From this equation we get v. Both cancel m both side and we get the v. So first write the equation. Net work done left side, right side change of kinetic energy. Here gravity force act in this direction, so this work done by the gravity is positive work done, and here friction force act, this is negative work done. And when the body climbs to this position, then gravity act in this direction, it moves in this direction, but that is net displacement in this direction, so here work done is negative. So this is net work done left side, we get net work done. Right side change of kinetic energy, we always write first final kinetic energy and initial 0. Now equilibrium of body. Equilibrium, there are three types of equilibrium: stable, unstable and neutral. What is the stable equilibrium? Equilibrium means net force is 0. Here force 0, unstable equilibrium, force 0 for every equilibrium. What is the stable equilibrium? Suppose this is a sphere and a ball is present at the lowest position, so this is stable equilibrium. Suppose this is a sphere and a ball is placed inside at the bottom of the sphere. Now when the ball is displaced a little, then it when the ball is displaced a little and released, then the ball returns to initial position. That is, the ball returns to its initial position. Always the displacement is in this direction, but the force acting on the ball is in this direction. That is, force and displacement, restoring force is opposite of opposite of displacement. Restoring force, that is this direction, restoring force this, and displacement is this, is opposite. What is unstable? If the ball is present at the top of the sphere, and if it is little pushed, then the restoring the force, the ball does not return back. The force is in the direction of x. Here restoring force is in the direction of x, so this is unstable. And neutral is, what is the neutral? If the ball is placed in the ground, this is neutral. That is, if the body is displaced, then it cannot neither move away from its initial position or back to the initial position. That is, what is stable equilibrium? When body is displaced, then it tries to back its initial position. When the body is displaced, then it cannot return to its initial position. And has neutral, if the body is displaced by little, then it neither move away or return back to its initial position. So these are the three equilibrium. Now for all the three equilibrium, force is zero. Here potential energy is negative. Here potential energy is minimum. Potential energy is minimum. Here potential energy is maximum. Here potential energy equal to 0. Now potential energy minimum. What is potential energy? Equal to du by dr. So du by dr equal to 0. 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 0. Now what is double derivative of greater than 0? For minimum, u is minimum, double derivative greater than 0, and this is less than 0. For this less than 0, and for this, so this is the condition for stable, unstable, and neutral equilibrium. Now collision theory. First, elastic, inelastic, and perfect inelastic. So what is the condition of elastic collision? Suppose a ball of mass m1 moves with velocity u1, and a mass m2 moves with velocity u2, and here collision take place. When collision take place, then this body exert the force and this body exert the force. So due to the action reaction, velocity changes. Suppose this velocity is v1 of mass m1, and this velocity is m2, velocity is v2. Suppose we consider first in general collision, that is collision in one dimension, collision in 1D. We consider first collision in 1D. Two body of mass m1 m2 moves with velocity u1 and u2, and here u1 greater than u2. After some time the collision take place, and after collision velocity becomes v1 and v2. Now what is elastic collision? For elastic collision, here momentum and for elastic collision, momentum and total kinetic energy both conserved. Conserved means before collision total kinetic energy, and after collision total kinetic energy and momentum both equal. Momentum before collision equal to momentum after collision. Kinetic energy before collision equal to kinetic energy after collision. And inelastic collision, momentum and kinetic energy, momentum is conserved. Momentum is conserved, but kinetic energy is not conserved. Okay, and perfect inelastic. What is perfect inelastic? Two body here momentum is conserved in all collision. Two body after collision stick together. That is, a block is suspended from this and a bullet is penetrate into the block. So after penetration, if this stick to the block, now if the bullet stick to the block, then both bullet and block combinedly move together. So this is the example of perfect elastic. Now for elastic collision, though, what is the condition? Momentum and kinetic energy both conserved. Here momentum is conserved but kinetic energy is not conserved. Two body after collision stick together. This is the perfect elastic. So here a term E, coefficient of restitution. What is the coefficient of restitution? The definition is velocity of separation to the velocity of approach, which is equal to V2 minus V1 by U1 minus U2. V2 minus V1 velocity of separation, velocity of approach is U1 minus U2. So E for elastic collision, E equal to 1. For elastic collision, E equal to 1. For inelastic collision, E less than 1. And perfect inelastic, E equal to 0. Perfect inelastic, E equal to 0. The formula, use the formula. What formula we use? M1 momentum conserved, M1 U1 plus M2 U2 equal to M1 V1 plus M2 V2. This is one equation, and second equation is E equal to 1, that is U1 minus E2 equal to V2 minus V1. It is two equations. So 1 and 2. These are the two important formula to solve the elastic collision problem. To solve the problem of elastic collision, we use for inelastic E equal to V2 minus V1, V1 minus E2. For inelastic, value of E is given. This is equation 1, and second equation is always this. So to solve the for inelastic collision, body comes from opposite direction, then we use final velocity is unknown in which direction. So as the two body moves from opposite direction, so total initial momentum before collision, we take this way minus, because momentum is vector quantity. If this is positive, this is negative, so total momentum before collision equal to this, and final velocity is unknown, so we can write in this way. If the velocity, this is positive, this direction we take positive. If from equation V2 comes negative, then that is final velocity of mass M2 after collision is in this direction, okay. So if two body approach to each other, then we take negative, and this is unknown. So if it is unknown, then we cannot assign, we cannot give the sign here, M2 is moved with velocity U2, and M1 is moves with velocity U1, and collision take place at here. But after collision, suppose after collision, M1 moves with velocity V1, and M2 moves with velocity V2, and this angle is theta 1, this angle is theta 2. This is given, that is from horizontal direction angle is theta 1 and this angle is theta 2, it is given. So what formula we use in this 2D collision? What formula we use here? If it is elastic, then here we use momentum along x direction. Momentum is conserved along x direction. Second, momentum is conserved along y direction, and third total kinetic energy is a scalar quantity. Kinetic energy is conserved. Kinetic energy is scalar, it has no direction, so we just kinetic. So here we can write three equation. So this is x direction and this is y direction. So first we find the velocity along x direction. This is v1 cos theta 1, this is v1 sin theta 1, and this is v2 cos theta 2, and this is v2 sin theta 2. And before collision, total velocity is along x direction. There is no velocity in this y direction. So we write here. So these are the three equation. Momentum is conserved along x direction, momentum is conserved along y direction, and kinetic energy is conserved. So if we write for one, what is the equation? If we write for one, momentum is conserved along x direction, so m1 u1 plus m2 u2 equal to m1 v1 cos theta 1 plus m2 v2 cos theta 2. We write this is equation 1. And for second equation, for second, momentum is conserved along y direction, so initially momentum along y direction is 0, 0 plus 0 equal to m1 v1 sin theta 1, this is positive, and m2 v2 sin theta is negative, so minus m2 v2 sin theta 2, this. So this is equation 2. And finally from 3, kinetic energy is conserved, so half m1 v1 square plus half m2 v2 square equal to half m1 v1 square plus half m2 v2 square. So here we can use the three equation, 1 2 3 equation. By three equation we can solve the unknown quantity. So suppose this is a ground, and a ball of mass m is initially moves in this direction u, it strike with a ground strike, and finally it with velocity v. If this angle, this is normal, now in collision this angle is not equal to this angle, so if this angle is theta and this angle is maybe phi, here theta not equal to phi, in collision these two angles are not equal. So suppose a ball of mass m is moving with velocity u, strike the ground, and after rebound after rebound after collision with the ground, the ball moves with velocity v, and the normal makes angle theta, and this angle is phi. So here what equation we can write? This is a ball and this is a ground. Here we know collision takes place between two body. So here one body is ball and another body what? Another body is ground. Ground is the another body. So suppose this is m1 equal to m, and m2 equal to mass of the ground, which is we take infinity, mass of the ground, and velocity u1 equal to u, this is u1, and u2 equal to 0, and v1 equal to v, and v2 equal to 0. So here we take the another body is ground, whose initial velocity and final velocity both 0. Now here important theory is present. What's the theory? This theory is very very important, and this theory is applicable for any collision. What is the theory? Theory is that here we draw a tangent. Suppose this is this ball and this is a ground. Now collision takes place at here. So this is tangent. If we draw a tangent between two contact body, between the two, if we draw the tangent along the contact surface and a normal, this is common normal, and this is common tangent. Cn means common normal, and CT means common tangent. Common tangent. What is the theory? Theory is that along common tangent, CT, common tangent, no change of velocity take place. That is velocity before collision equal to velocity after collision equal to velocity after collision. So this theory is important. So along the common tangent, no change of velocity. Now, so for general case, when this type of collision take place, m1 moves with velocity u1, m2 moves with velocity u2, and collision take place here. Here, common tangent is in the direction. This is common tangent, and common normal is in the direction. Common tangent. We know that velocity take place along common normal. No change of velocity. That is velocity. No change of velocity take place along common tangent. So there is no change of velocity along common tangent, but change of velocity occurs along common normal only. Along common normal velocity changes. No change of velocity occurs along common tangent, because here velocity v1, v2 take place along this direction. Along common tangent, no change of velocity take place along common tangent. So this theory is very important. Along common tangent, no change of velocity take place. Why? Because impact occurs always along normal. No force acts along common tangent. So as there is no impact along common tangent, or no force act along common tangent, so there is no acceleration along this. So no change of velocity occurs along common tangent. Along this v sin phi and this v cos phi. So theory is that along common tangent, no velocity take place, so no change of velocity take place. So u sin theta, initial velocity, and final velocity is v sin phi, both equal. Velocity is same before collision. Along common tangent, velocity is this, and after collision, velocity is this. This will equal to this, because no change of velocity occurs along common tangent. Velocity of separation or velocity of approach. Case coefficient of restitution equal to velocity of separation by velocity of approach. Separation is, that is u1 minus velocity v2 minus v1, v2 v2 0, v2 minus v1 0 minus v cos phi equal to u1 minus u2. u1, what is u1? u1 is minus u cos theta, because it is moved downward. u1 minus u2, so equal to e. So from this we get v cos phi equal to this. Now if we divide 1 divided by 2, we get 1 divided by 2, this divided by 2, we get tan theta tan phi equal to this divided by this, u sin theta cancel, so tan theta by e, this by this, sin theta by cos theta, tan theta by e. So tan theta equal to e tan phi. This is one equation, and if we squaring and adding, we get another equation. Squaring 1 square plus 2 square, we get v square plus v square, that is v square sin square phi plus cos square phi equal to u sin theta whole square plus e u cos theta whole square which is equal to, from this we get v equal to root over u sin theta whole square plus e u cos theta whole square, which is equal to u into root over sin square theta plus e square cos square theta. We get these two results, v equal to this and then. So for oblique collision, that is collision with ground and the body, we get two equation, we get two result. Yeah, student, this is the end of the class today. To get more important problems of NEET exam, subscribe my channel. Okay, thank you.